Think forward. Think Research Channel.
Thank you, Mark. And it's indeed an honor and a privilege to be able to have this opportunity to give a talk in my area of research to the larger university community. And because of the audience are more of a general nature, so my talk would be also more leaning toward the more layman aspect of power electronics and what is the relationship with energy and the environment. And I listened to a talk several years ago from Vice President Gore in the White House. And he vividly depicted this picture, which is very simple. He said, you look at the human history for however numbers of years in the past, but you look at the energy consumption for the human beings and during the last century. And everything else we did prior to that was pale in comparison with the amount of energy we consume over the last only short 100 years for the human history. And so is the electrical energy. If you look at the electrical energy consumption today, it is consumed at the average rate of 10 billion kilowatt hours every day of every year. Just awful lot of large numbers in terms of the electrical energy. And if we look at the population growth from now to year 2020, this project the 20% the energy consumption during the same period of time would be about 50% increase. So we are consuming more and more energy as we go. And what is it exactly is environmental impact, the large amount of energy we consume. You look at the carbon emission, and that is increasing at an average annual growth rate of 2%. So for a span of short 35 years, we're going to emit, the carbon emission will double within 35 years. If you work out the math, what happened in the next X hundred of years, what is going to happen in the carbon emission? So the global warming effect is real. And I do not think we can allow this to continue much longer. On the other hand, you look at the developing country, the energy consumption is growing so fast, and you look at the third world, the energy poverty. And they actually pollute the environment in a different form because of shortage of energy. So in the long run, the health of the economy is dependent on the health of the ecology. Synergistic solutions are needed, and environmental friendly product can be and should be made competitive. So if we look at the source of energy, again, going back to the history in the 19th century, essentially came from burning wood. We chop a lot of trees. In the early part of the 20th century, and we started consuming lots of coal. After that, oil, and gas. But you see a general trend is if you add all the energy from different sources and add together, the energy consumption is growing at a very fast rate. However, on the other hand, you see the decline of these consuming of these different forms of energy simply because of the limited resources we have in this planet. Now, in light of this, you can see that the hydraulic energy, the hydro, actually, which is more environmental friendly in some sense, is only a very small part of the total energies, and so is the nuclear. So in light of the energy growth in general, and then the decline of consuming these limited natural resources, what would have to happen in the future? That is, we have to look for other forms of energy, and mostly would be coming from the renewable energy such as the wind, the photovoltaic, and other. You look at the cost of electricity today, the more traditional power generations come from coal, the crude oil, the gas, and the nuclear, and so on. They are actually rather inexpensive forms of energy. Very recently, the wind energy becomes competitive in cost, and we see a rapid growth in the use of wind energy. Photovoltaic energy is coming at a relatively higher cost, and it has its own niche market, a certain place where you can have the energy made available from other more conventional form, and solar energy is a possible solution. The fuel cell, hydrogen energy, is coming at even a higher cost, and other forms of energy then are available today, but even at a higher cost than fuel cell. So let's take a look at the green energy. It comes in how many different forms? The solar, the wind, the hydrogens, the biomass, geothermal, tidal powers, and hydroelectric powers. Because of time, I can only cover several aspects of this. You look at the wind power, today it already generates a $7 billion industry with annual growth rate of 15 to 25%. And you look at what is in wind power, and you open in the back of that is a wind turbine together with lots of power electronic gears that controls the wind turbines, that convert the wind turbine energy in the forms of electrical, and then provide the proper interface with the utility grid so the wind power can be integrated into the more conventional form of electrical power. So this picture shows that over the last 20 years or so, the growth of use of wind power is at very, very fast rate. So if you look at year 2002, altogether we have installed 32 gigawatts capacity. And projected by year 2010 would be 180 gigawatts. Year 2020 would be 1,200 gigawatts. Look at the solar power aspect. What we know of today is basically the silicon-based solar cells. It's a mature technology because it's using the silicon wafer and using the process of making semiconductors, so it's a relatively expensive process. What is coming very soon is the thin film process, where you can use a different, instead of the etching, you can use sputtering and so on to have to generate a solar cells, and these comes at a lower cost. What really is promising is in the future, I'm talking about the future, might be 10 to 20 years away from now, is the organic fuel cell, a solar cell, which in the forms of polymer organic, and you can make fuel cell like you print papers. And that really would make that cost come down into the form that could enable the widespread use of the solar photovoltaic. And hydrogen power has been talked a great deal in recent years. If you compare hydrogen power, the fuel cell, with the more conventional power in terms of efficiency, the gas turbine, the steam turbine, the diesel generator, and so on, are usually in efficiency of conversion efficiency of 20 to maybe 40% range. So it's not very efficient energy source. Fuel cell comes at about 50 to 60%, but a combination of fuel cell with the, for example, gas turbine would increase the conversion efficiency to 60 to 70%. What does that mean? Here you look at the bottom line, basically say 1 percentage point of efficiency improvement on a utility grid worth $1.2 billion. So So if you translate that improvement of conversion efficiency in terms of economy, that's a huge impact. And here is an example of what we did in the aspect of the fuel cell research. We have developed a converter that powers the fuel cell project funded by Ford, Daimler Chrysler, EcoStar, and later on was purchased by Ballard. Ballard is the world's largest fuel cell company. And we built a converter today is being manufactured and used in every fuel cell test vehicle made by Ballard. Here's the pictures of the Toyota Prius, which is very highly publicized. If you look in the lower right corner, then you see the fuel efficiency is about 65% of energy saving in comparison with the IC 1.5 liter IC engine. So that's again talks about the fuel economies. And in here, in this hybrid electric, I'm sorry if I say fuel cell, there's no fuel cell in here, it's just hybrid electric cars with the part of the IC engine, part of the electric drive system. So if you look, open the hood, you see lots of power electronics under the hood. And here is one example of what we did for the big three company, Ford, General Motors, and Daimler Chrysler, and then also the U.S. Army TACOM on a project funded by the government, PNGV, Partnership in New Generation Vehicle. We developed a number of different inverter drives that can go into the hybrid electric vehicle. And this is interesting pictures and really an artist's renditions of what the future energy world is like, and where the living beings can exist with its environment harmoniously, and where you see clean airs, clean waters, the fish are happy, the birds are happy, lots of windmills generates a lot of solar cells and thermal generators and so on and so forth. And our living standard doesn't have to suffer. In fact, it looks pretty impressive. A picture. Now, you look at the power aspect of it. What it takes to make that happen is a distributed power generation concept. So where in this picture, you will see that you may have a more traditional power generation plant, then you have a wind generator. Wind generator, you have a photovoltaic energy source, you have a micro turbine, and you have the fuel cell as an energy source. All of them are work together and integrated into the utility grid and deliver that electric power to the users. And if you look at here, other than the traditional forms of generation plant, every other forms of power generation requires a considerable amount of power electronic to integrate that source of energy into the utility grid, so that the user would not even have to notice where they draw power from. So, coming to the point of a power electronic, how is power electronic related to energy efficiency? If you look at the total energy, on the left-hand side, 40% of the pie is in the forms of electrical energy. According to EPRI, this is the Electrical Power Research Institute, in 1977 report indicating 40% of those electrical energy has to be processed, controlled, conditioned before it delivered to the end user, and 60% of them is simply just delivered directly to the end user without any forms of control and conditioning. So who are the end users? More than 50% of that is in the forms of rotating machine, motors and motor drive. And 20% of that is in the lighting. And 10% of that, which this part is growing very rapidly, is the internet infrastructures, the computer, the data handling, and so on and so forth. And that part is growing very rapidly. And the report also indicated by year 2010, 80% of those electrical energy would have to be processed and controlled and conditioned before it delivered to the end users. Now, the key point is, if we are using power electronic solution to control, conditioning, processing the electrical energy, we can save roughly about 35% of that electrical energy being passing through the power electronic devices. And that impact is very significant. I'll just give you an example of that. In lighting, because lighting represents 20% of the electrical energy, if you simply change the incandescent lamp by fluorescent lamp, you probably save somewhere around 4 to 5 times in terms of energy cost. Now, the fluorescent lamp today, most of them are operated with magnetic ballast. This is a chunk of ions, and the lamp has to work with the ballast in order to be able to operate. Now, if we change simply the magnetic ballast by electronic ballast on the left-hand side, you save about 30, 33, 35% of energy, and that is simple. So what does it take for power electronic solution to be widely used in those providing energy efficient solution? It really is the cost issue. Are we able to make electronic device as cost effective as the non-electronic solution? Look at the other form, the impact which is even more significant. Look your air conditioning unit, the heat pump in the house, the washer and dryer, and the other white goods in your house. Most of these things are driven by a constant speed drive, not a variable speed drive. You notice that in your air conditioning unit, you hear the thermostat doing the control, the regulation, so click on and off, that in terms of click on and off the compressor, then and drive that and making it operate. So you're constantly doing on and off control of that. So what would be a power electronic solution? You don't do that on and off control. You leave it running all the time, but you change the speed. You need more cool airs and you run faster. You don't need it and you run slower. And that alone can save 35% of energy consumption. So today, variable speed drives are pretty complicated electronic gears. And if you look at the product, is of this form, very complicated and expensive to build. It is roughly the initial cost of constant speed drive compared to a variable speed drive compared to a constant speed drive. The cost factor might be 2 to 3 times. So that's why people are not buying it today. Almost zero the residential use purpose of air conditioner or heat pump using a variable speed drive in this country. But in Japan, in Europe, you begin to see the consumer, the residential application for variable speed drive or heat pump, washer and dryer and things like that. And so if we are able to make a power electronics solution more affordable, we can open a large market which would be 10 or even 100 times higher than what the power electronic market is today. On the other hand, I think we are facing another issue of a crisis proportion. And you look the way the power electronic equipment are made, and you look the typical product in the lower right corner. It consists of hundreds of different electronic components. 40% of them has to be manually inserted in the print circuit board. Only 50-60% you can use automated machine doing auto insertion. So there are so many labor involved in making those products. And because of that reason, about 10 years ago, the US industry started taking the outsource strategy for manufacturing facility. And so on, we have lose our manufacturing base in a very alarming rate. And still, as of today, there is no sign of reaching an equilibrium other than being zero, if we allow it to happen, or bring the manufacturer base upward. So that comes to the CPAS vision and challenges. What we want to do is to model after the microelectronic industry. And microelectronic industry is governed by Moore's law, which basically said every year and a half, you can reduce the cost by half if you keep the same performance. Or you can, if you want to maintain the same cost, your performance will be double. And that law is working so effectively for four decades, and therefore create a $1 trillion industry. What about power electronic? Can we model after that? We don't quite have a Moore's law, but if you look, what underlines the success of Moore's law is a standardization, modularization, integration, continuous improvement in manufacturing, and a continuous increase in volume, therefore the costs come down. So if we follow those aspect of it in power electronics, doing more integrated approach, standard modular approach, we can also unearth a large market, which today is not being used because of the cost associated with that. So our vision is to turn this thing around, so in the future we don't use labor to manufacture power electronic equipment. Instead, we can do an automated manufacturing of modular, standardized modular approach, and you only need a few modules like this to make a system. Instead of hundreds of parts, you only have several components. And so the labor involved in putting them together would be minimal. So the center, how do we do this? And today there is no single university anywhere in the world that has the capability to address all the critical technological issues. So our strategy was to team up with the university with complementary expertise. For example, University of Wisconsin Madison is probably one of the, if not the most well-known in the world in terms of their capability of design motor drive system. Rensselaer Polytechnic Institute is one of a very few universities that has a strong power semiconductor device capability. And Virginia Tech is very well known for its power conversions and system integration aspect. Together we have North Carolina A&T and University of Puerto Rico. And what it makes our center rather unique is we have a large industry consortium behind us to support our vision and willing to work together with us to realize that vision. Of course, our center's mission is not just research, but also the education outreach and the tech transfer. And here shows where the 78 members coming from, so all over the United States, and in fact, a large number of them are coming from European side and Asian side as well. Now, center research program are structured with the 3 tiers of research activity. The lower level is the basic research, the fundamental knowledge plan, where we have advanced research thrust in advanced power semiconductor device that's led by Professor Paul Chow of Rensselaer. And integrable material, we're talking about material that can be used to integrate power electronic module together. And that effort is led by Professor G.Q. Liu from Material Science Engineering, Virginia Tech. And the high density integration of how to put everything together in a modular fashion. This effort is led by Professor Van Wyk, Virginia Tech. And the thermomechanical integration aspect of that is led by Professor Scott, Virginia Tech, Mechanical Engineering Department, and Control Sensor Integration by Professor Lawrence from University of Wisconsin. In the enabling technology area, we're really talking about how to integrate power electronics in a modular fashion. That effort is led by Professor Tom Johnson, Professor Tom Lipple from University of Wisconsin. And above that, the system level, which is basically take all the input from the basic research, the modular enabling technology, integrate them together in the system level. And that particular research thrust is led by Professor Dusan Boryevich, Virginia Tech. Because of time, I'm going to quickly go through this. Is just an example of illustrating how do we integrate things together. In the electronic circuit, all the semiconductor parts, the resistor, capacitor could be integrated together in a module fashion using the multi-chip, multi-layer structure. All the passive components, large, bulky inductor, capacitor, transformer, and so on, also can be integrated into a single modular fashion and using the multi-layer structure. And this is a pioneer effort done by Professor Van Wyk. The very unique research activities done. And here is showing how Dusan would be able to put everything together. Here on the left-hand side is a more conventional circuit. Now we want to do a more integrated approach. Here is the filter now become one component integrated together in one module done by Professor Van Wyk. And then all the semiconductor device control ICs and represent hundreds of parts now is again reduced into one part, one module. And all the passive components on the secondary side are again integrated together in one module. So if you all look at the right-hand side, to make a system, it only takes about less than 15 or so components, while on the left-hand side it takes hundreds of components. So we already have demonstrated that integration concept. And here's another effort. What do we do with the motor drive? We take a very complicated electronic equipment, which is usually done discretely in this fashion, and we integrate them into a multi-layer structure, become one component. We put them in the industry standard package and form factor, and with a plastic case, that become one component. And that component represents function of hundreds of components. Our effort actually goes beyond just what industry NSF is supporting us. In fact, we have really all-out effort and looking at application from different domains, because more than 50% of our support comes from industry or other government agency, and the other 50% comes from NSF side of it. So if we put all the effort together, we have this modular integrated approach that covers a wide range from low power, 10 to 100 watt, to medium power, 1 to 10 kilowatts, to high power, 10 kilowatts to 10 megawatts level, in using the similar concept in building the power electronic system. And because of time, I'll just quickly give you one example. In the low power part, and in order to power a microprocessor, this is the motherboard of a computer. Microprocessor will be plugged into this socket. What's around that is a power supply that powers the microprocessor. And today, every microprocessor is powered by a power supply with a technology developed at Virginia Tech. And this technology actually from the beginning seems to be very complicated technology, but within a year time it is being adopted by the entire industry as a practice, because they were convinced this seemingly more complicated, expensive technology actually is much more cost effective than the existing technology. So how do they make it so cost effective? They do a large amount of integration. All the controllers are integrated into one control IC. All the power devices are integrated into the modular approach. It is exactly the concept we've been promoting. And we have, now today, you look how many companies produce this product and selling in the marketplace. Almost every major IC company. And how many companies have produced the modular approach for the power electronic part? Quite a few. And it is because of the integration, standardization, make that a very cost-effective solution. One last thing I want to share with you is one of our former graduate student, Ashraf Lotfi. He co-founded a company. He has recently announced a product. It is the cutting edge of the technologies and the front of the pack. Now, the degree of integration he was able to do is he integrated not only all the semiconductor device together, but he also integrated the passive components, such as a magnetic, on the backside of the substrate. He can integrate the magnetic. So what he has a product now is a fully, completely integrated power electronic system solution. And you buy this chip and you plug in the board, and it works. And so what had happened is, in our effort is, we have, based on our technology, we have created a multi-billion-dollar industry that all aim at power management solution for this generation, next generation microprocessor. My time is up. Thank you very much.